Welcome, dear friends of protection, control and electrical engineering. Last time we created this beautiful grid that you can see here, this primary system, which depends from two substations. We have substation A and substation B, and which we are able to connect in case of maintenance works. But let me just open the couplings for this time. And today I'm going to show you how you are able to add current transformers and voltage transformers and protection relays. Okay, just let's get started. We begin with one current transformer. Oh no, let's start with the voltage transformers, okay? First of all, I always start with the three-phase voltage transformer. Here you can see this one, we rotate it right. And then we connect it to the bus bar. Let's give it a name. We just call it voltage M VBBA. Okay, we don't show the label, and everything is perfect here. We don't have to do anything else. Okay, second one, we need a voltage transformer for, how do you say it in English? We call it open delta, broken delta. I think you say broken delta. Okay, if we take the voltage transformer for the broken delta winding, we just rotate it twice and connect it as well to this bus bar. Maybe let's put it first here and then shift it over. Yeah, okay. And we call it, let's call it voltage broken delta. I hope this is the proper name. You guys can write it in the comments if you have better ideas. I'm not sure, but I'm just call it broken delta now. Okay. And now we need current transformer. Let's take first of all for the three phases, turn it around, and you can toggle the earth, which should direct to the protected element, which is our bus bar. And now I take everything and put it a little bit down. Yeah, this is also not the best way to show it. Okay, and because I need some space here, let's put this to the top again. This probably as well. Okay. Let's put this to the top. And now we have enough space here for our CTs. And we start with this phase CT, which will be connected here. And as you can see, both elements are still yellow, the switch and the current transformer, because they are not connected yet. And now we just add another, no, not this one, another current transformer. And this time we need the current transformer for the 3-volt zero sequence system current. And this is of course this one with the little n on it. We just rotate it a couple of times, toggle the earth, and just connect it to our application. Perfect. Just let's put it somewhere over here. And this looks pretty good. Okay, last component that we're going to need is an relay. Just let's take this relay. Let's name it like MV busbar A in feed. And now we just have to connect this relay to all these 4 transformers, and this is done, I know 2 ways. The first way would be to mark the relay and push the configure device button. Everything gets mysterious then, and now you can prepare here everything, or let's go back with escape. Or you can also double click on the relay and the same will happen. Okay, now you just have to click all the things, the elements that you want to connect to your relay. In our case, these are these 4 transformers. We also could use here all the switches and so on, but this is not important for our job now. Okay, and now always if you mark the relay, you can always see this color which tells you that these elements are connected to this relay. Okay, that's pretty good. And now we still have to connect everything to our CMC 356, because if we don't do so, we are actually not able to calculate anything, since this software is a test software and not a calculation software. Okay, let's close the switch again here. And okay, so let's do this job here. RelaisSim-Test has here a very, very powerful button. It's auto connect, and I love this. I love auto stuff. Yeah. If I have to tidy up my room, I like this button that I push, tidy up, and everything is tidy up. It's just perfect. And in this case, I just click auto connect, and everything is connected. That's real magic. Okay. When it's done, then we can go over to the test manager. And as you can see, we have no test case added yet. And that's what we're going to do right now. We add a test case and just open this test case. Perfect. And as you can see, here are the first EMT waves available, because this software already is calculating. It's already working. Okay, it's magic. Okay, so let's put this all the way down that we are able to see our grid model here again. What we first want to do is, on this blank left side here, we are able to arrange our measurements for the CTs and for the relays and so on. And for that, we just have to, let me just zoom a little bit in that I can show you this much better. Let's get started with our zero sequence voltage, or with the broken delta voltage that we measure for the entire bus bar. And you have here this little pin symbol, and just click on this needle, and here the measuring will appear. And we also want to see the primary voltages, so we just check this box here, and now we can see the primary and the secondary voltages that are measured on our broken delta windings. In our case, we have nothing, because we don't have an earth fault yet, because we have the perfect voltage and we have a perfect load current. So there's no reason that the zero sequence voltage should rise up. Okay, now we want to see the current of our split core CT. For this reason, we also just go on this pin, we pin it to the dashboard and say, yes, please also show us the primary currents. And here it's the same. If there is no zero sequence voltage, then there's going to be, of course, no zero sequence current. Okay. Next step, we want to see the relay by just pressing pin values to dashboard again. And let's also customize this a little bit. I always want to see the phasor diagrams. I love phasor diagrams. Everybody knows that I'm in love. I felt at the very early age, I felt in love with phasor diagrams. We have this voltage primary, currents primary, and we also want to see the voltage and the currents of the secondary side. Perfect. Okay, that's all by now. And let's make the model way smaller again, that we have the view from the eye of a bird, a flying bird, of course, not a bird sitting somewhere in the basement. We are talking about birds that are flying over a scene and see everything perfect with their eyes from the top. You know what I mean. Okay, you know what I mean. Okay. all we need now to become the most happiest people in the world is, of course, an fault. And now we add a ground fault, and I want to add this ground fault on this line here, and I want to have it somewhere, let's put it to the start at 0%, and I like to have this ground fault in second phase, because then I get this beautiful colors here is blue and red, and is really, really good for our eyes. Okay, and now you are able to switch here for the fault-free area, and you can also click here in this faulty area, and you can see how the phasor diagrams change just by clicking in this different ranges. Okay, and here we can see already that our voltage, the blue arrows are our voltage from phase 2, is broken down to almost 0. As we can see here, there are just a couple of millivolts still remaining, and that our fault-free phases increased by the root of 3 by 1.7231, and also the angle between is squeezed together. Before we had 120 degrees, and now we only have 60 degrees, because each side goes 30 degrees to the inside. Okay, and we have still this current flowing, and that's real magic, because we are in an insulated system, and an insulated system always says that the load current is not affected. All these low voltage loads here are supported by energy, and nothing bad happens. Okay, so the customer here on this low voltage side won't realize that there are any problems in the grid, and everything works quite perfect. So let's have a look to our zero sequence signals. We have here the voltage of the broken delta. Let's put this to the top, and we have here the current transformer, which is the split core transformer, which is sitting here in our in-feed. Okay, and now we want to see here this first moment when the earth fault occurs, and what we can see here is that the voltage amplitude is negative and the current amplitude is positive. And if this both have the opposite direction, then this means that this relay sees the fault or the ground fault in forward direction. This criteria is usually used for the transient earth fault criteria, which we don't have here yet, but I just want to show you this because this is remarkable and this is very, very important. Okay, and now my question to you is, what happens if let's assume this this second substation is out of service, it's out of order, and I connect all this capacities here to our grid on this A side. And now is my question, what happens? Because usually if we put more cables to the grid, the capacitive ground current should increase. And now my question is, what's going to happen if I close this switch? Will this amount of 3.2 or 6 amps, will this amount increase or will it decrease, or will there be no change? Who's able to answer this question? Just think about it short and I will tell you the answer, because everything what is behind of this measuring point, and this here is all behind this measuring point, will be deducted again. So you have to think about like this. The capacitive current flows in the earth and flows back via the ground fault and will be flowing twice through our split core transformer. At the first time it flows in the forward direction, and at the second time it will flow in the backward direction. So every time a current flows through the split core transformer in two separate directions, it will result in compensation. So the current disappears. So I tell you, if we close this button, nothing will happen, just a little bit. So let's see, we close this button, and as you can see, we almost have the same current here. Okay? And this is the first thing that we have to learn. For this point here, for this in-feed, it doesn't matter how we switch our grid here. I can even open this switch here, and all these cables are not in the game anymore, but you can see we still stay at this amount. And where comes this amount from? Of course, everything what's in front of our split core transformer is. Everything what's here. And we have here about 500 meter cable in a double system. We have two systems. That means we have 1 kilometer, and 1 kilometer is always about 2, 3 or 4 amps by kilometer. Okay. And for this reason, everything what we see here, this 3.3 amps, are the capacitive components of this area, or let's say of this in-feed here. Okay. Okay. And now we want to see what happens if we add here another relay and here another relay, and if we see a little bit deeper into the grid. And for this reason, we just go back to our power system. We have already the voltage, so all we need now is to add another relay which measures here this 3-volt zero sequence current. And for this reason, we need again a split core transformer. Here, this is the little one with the N on it. We just rotate it, and we have to toggle the earth again, of course, and then we can put it inside. So for this reason, just let me delete this connection here, put it in, and place it on a proper place. Perfect. And here we have the same. Let's put this a little bit down and delete this area and add another split core transformer, toggle the earth, turn it around, and connect it as well. So what we have to do now is, of course, we need the proper rating for it. Oh, that's what we forgot for our first one here as well. We have here 60 amps by 1, okay? We just do a good job in putting all this 60 amps values here inside, okay? That's all, and now we just add another 2 relays, this one, and we duplicate it to another one and this one. And now we just say that this relay sees this CT and this relay is connected by this CT. That's everything. Let's go back to our hardware configuration, push our magical button again. Everything is well connected, and we can go back to our simulation test. Okay, so as you can see, we have now another split core relay here and another one here. Here where we see no signal, this is this one, of course. It's the 3 because the switch is opened. And we can see that both the in-feed here, this current transformer and this current transformer, have the same direction and the same amount. Probably it's a good idea to pin also this values that we can see it here. Hang on, I need it just once on top again. Okay, perfect. And we want to see this as well and put it to this place. Okay, and we want to see, of course, the currents of the primary side. And Okay, here we have here's no fault, and now we go to the faulty side, and as you can see, and now we also get the proper results for the secondary sides. As you can see, we're talking about 54 milliamps here, so it's a very, very small secondary current that we have here, and we have to take the half of this value to get our starting value, so that's very, very small. Okay, and now we want just to have a look at this current here, which is the current of this CT. And my question is, what's going to happen with this current of 3.3 amps if I close this button now? Will this affect this measurement or will it not? Just think about for a moment. I told you everything what's behind the measurement point, so everything what's behind here in this area doesn't affect it. But now we want to see what happens if something will be added which is before this measurement point, and we are connected here before this measurement point. So to cut a long story short, we will get a significant increase of this value. Not this one remains the same, but this one here will increase extremely. Let's have a look. We just close the switch and see it went up to 9.5 already, 9.5 amps. That's a big jump that we just did. And this is just because all these capacities here are just now added to this measurement point, because all these capacities also flow back via this ground fault point through our current transformer, but they only flow one time through the current. Okay, first time they come from here, and second time they flow through our CT, and that's the reason why we can see it in this measurement by now. And if you have a look here, this 6.2 amps are added from here, and the other 3 amps that we have are from here, and this is the entire grid. And if you want to determine the smallest value for your relay setting in order to make sure that you have a proper starting amount, you can just take this amount here, or you can even look if you find another combination with the smallest capacity available, and then you can say I take the half of this value, and then you have a perfect starting value for your ground fault measurements. Okay, thank you for watching. That's all. I hope you learned a lot and I could show you how perfect this software is. I don't get a dime by Omicron to show you this software. I just did it because I love this software so much and I work with this software for such a long time. Thank you for watching. See you soon and bye bye.